Why use a tangent line approximation? Well, sometimes it's easier to use the tangent line to get a function value than to actually plug into the function value itself. And the reason we can use the tangent line is because the closer you are to point of tangency, the more the tangent line will approximate the actual function value at that point. So what I'm going to do is I'm going to show you with Desmos here. We'll use a simple example of x squared, and we'll show you what happens when we try to zoom in, and we'll use the 0.11. All right, so let's start out with this example, y equal x squared. And let's find the tangent line at the point 1,1. Okay, so to do the tangent line at the point 1,1, I'm going to take y prime. So y prime in this case here would be 2x. I'm going to plug in 1, so I would get a slope of 2. So that means in point slope form at the point 1,1, my tangent line would be y minus 1 is equal to 2 times x minus 1. Okay, so let's put that into Desmos. All right, so we can put it in point slope form. Y minus 1 is equal to 2 times the quantity x minus 1. And we have our tangent line there. Okay, so tangent line approximations work when we have values that are close to 1. All right, because as we zoom in, the tangent line almost mirrors the exact image of the curve. So for example, as I zoom in here, we can see that that tangent line is almost identical to the curve when we zoom in. Okay, now the farther away we get from the point of tangency, you can see the separation. So you have to be close to the point of tangency in order to use this as an approximation. Okay, so that's the concept of tangent line approximation and why we use it. And then we'll do an example next. All right, so now we're going to find the equation of the tangent line of f of x at the point 0, 1 and use the tangent line to approximate f of 0.1. All right, so first off, what we're approximating, so in this case here, 0.1, we have to realize that the closer it is to the x value of the point, the more accurate we're going to be. So in this case here, 0.1 is very close to 0, so this should give us a pretty accurate estimate. All right, so what I'm going to do is I'm going to get a tangent line at 0, 1. So I'm going to take f prime. And it looks like we have the product rule along with a chain rule here. All right, so the derivative of the first would be negative sine x times the square root of x squared plus 1 plus the derivative of this, which would be 1/2 x squared plus 1 to the negative 1/2 power times 2x, and then we can't forget we have to also multiply by cosine x. All right, so that means that f prime would come out to be negative sine x times the square root of x squared plus 1. And then this is going to simplify to x over the square root of x squared plus 1 times cosine x. Okay, well, we need the slope at 0, so we're plugging in 0. So we get f prime of 0. And here f prime of 0 would come out to be sine of 0 is 0, so this is 0 if we plug in 0. And then we have an x up here. So this would also be 0, so that means the slope is 0. So that means my tangent line in point slope form would be y minus 1 is equal to 0 times x minus 0, or in this case here, this simplifies to y equals 1. So that means that at anything close to 0, the tangent line approximation is going to come out to be 1. So what I have here is f of 0.1 is approximately 1 by using my tangent line. All right, so what I'm going to do is I'm going to do this on a calculator and we'll see how close we are. All right, so I put the problem into Desmos and we can see that if I plug in 0.1, I get 0.9999 continued on, which is very, very close to the approximation that I get of 1 from using the tangent line. All right, let f be a differentiable function. Estimate f of 2.1 given that f of 2 is equal to 1 and f prime of 2 is equal to 3. All right, so what we're going to do is we're going to use the point 2,1. So we're going to get the tangent line at the point 2,1, and then we're going to use that, and we're going to plug in 2.1. All right, so we have the point 2,1. We know that the slope, f prime of 2, is equal to 3. So we know that the slope is 3. So in point slope form, this would be y minus 1 is equal to 3 times x minus 2. And at this point, when you're doing tangent line approximations, a lot of times it's easier to leave it like this to start, because what we have to do is we have to take 2.1 and plug it into the tangent line to get our estimate. So we would get y minus 1 is equal to 3 times 2.1 minus 2. So that comes out to be y minus 1 is equal to 3 times 0.1. So that means that y is equal to 1.3. So that means using our tangent line, f of 2.1 in this case is around approximately 1.3. All right, so let's finish with an AP-like problem. Let f be a function that is differentiable for all real numbers. The table above gives the values of f and its derivative f prime for selected points x on the closed interval -1.5 less than or equal to x less than or equal to 1.5. The second derivative of f has the property that f double prime x is greater than 0 on this same interval. Write the equation of the tangent line to the graph of f at the point where x equals 1. Use this line to approximate the value of f of 1.2. Will this approximation be an under or an over estimate of the actual value? Okay, so we want it at 1.2, so we're going to use the tangent line at 1. So that means we have the point 1, -4, and we have a slope of 5. So that means in point slope form, we would get y plus 4 is equal to 5 times x minus 1. We're going to plug in 1.2. So we would get y plus 4 is equal to 5 times 1.2 minus 1. So we would get y plus 4 is equal to 5 times 0.2, or y plus 4 is equal to 1. So y is equal to -3, which means that f of 1.2 is approximately -3. Okay, so now they want to know, will this approximate be an over or underestimate of the actual value? Okay, so what we need to understand is our tangent line here, and what we're going to look at is the concavity. So when a function, I'll do this at the top here, when a function is concave up and we connect a tangent line to it, we can see that the tangent line actually is tucked underneath the curve. So as we move away from the curve, away from the point of tangency, we can see that the tangent line's value is a lot less than the curve. Okay, so that means when the function's concave up, it's an underestimate. And then if you had your function as concave down, and we connected a tangent line to it, the opposite occurs. This becomes an overestimate. Okay, so now what's the concavity here? Well, this is why they had this last sentence. The second derivative of f has the property that f double prime is greater than 0. Well, if f double prime is greater than 0, that means my function must be concave up. So that means that this would be an underestimate. And to justify on the AP test, all you would have to say is because f double prime is greater than 0 on that interval. Okay? Thanks for watching. I hope you enjoyed the video. Please like and subscribe.